When Einstein published his theory of general relativity in 1915, it left a bunch of questions unanswered. One of them, why do conservation laws only sometimes work? Noether's theorem provides us with an answer. Conservation laws describe measurable quantities that don't change in any system where no external force is applied. One such quantity is energy, which according to the law of energy conservation can't be created or destroyed, although it can transform from one type to another, like when the mass of a pendulum moves from its highest position to its lowest. Another is momentum. Conservation of momentum is the principle that a body or bodies in a system will keep their total momentum. So a hockey puck with constant mass sliding on a smooth, frictionless surface will have constant momentum throughout and therefore constant velocity because P equals mv, or the sum of momentums for two hockey pucks that crash into each other will stay the same even if their individual momentum changes because one of them slows down and the other speeds up. Up to when the theory of general relativity was released, it was believed that conservation laws were always true, but Einstein's math described a failure of energy conservation, a result that was validated in 1929 by Edwin Hubble's discovery of redshift, whereby light waves are stretched as the universe expands. Their wavelengths become larger and shift towards the red, less energetic side of the visible light spectrum. As a solution, Noether offered her eponymous theorem, which reveals a relationship between conservation laws and a more fundamental property of nature. It explains why conservation occurs, thereby helping us understand why it fails. This more fundamental property? A continuous symmetry. Something is continuously symmetric if it stays the same for any transformation in a given coordinate system, like a perfect sphere, which is continuously symmetric under rotational translations. No matter which way or how much you rotate it, it looks the same. This is as opposed to a discrete symmetry where only certain changes will keep the object looking the same. Mathematically, continuous symmetry is a quantity in the equation that you can change without changing the equation itself. For example, if you replace x with negative x in the equation y equals x squared, the equation doesn't change. Noether's claim is that for every continuous symmetry in the universe, there's a conserved quantity. For symmetry of spatial translation, there's conservation of linear momentum. If you add some number to the term in the equation representing position, the momentum does not change. Symmetry of angular rotation leads to conservation of angular momentum. Symmetry of time translation leads to conservation of energy. In practice, I have translational symmetry if I can do the same experiment anywhere and the result is the same, which isn't actually totally true. Imagine I'm standing at point X in my room and then I move over to a new position 2 feet over, but there's a desk there. That desk will get in the way of the experiment, so the ball won't fall the same way as it did at point X, so you have to move the entire system. And symmetry of time means that it doesn't matter what time of day I do an experiment, the energy is conserved. Neither of these things should be revelations to you, and you probably take it for granted that the ball from our earlier example falls the same in the morning as it would at night. But in the universe Einstein describes, you can't take for granted that the dimensions of space and time are constant. Instead, they're malleable and changing, so time symmetry is broken. If we know that conservation laws exist because of continuous symmetries, then it makes sense that when symmetry of time is broken, so is conservation of energy. So next time somebody tells you energy cannot be created or destroyed, you'll know that's not the full truth.